Hey, physics friends, and welcome to 2.5, which is the last lesson in Unit 2. And I've entitled it Flexing Position versus Time Graphs. What I mean by that is I'm going to do a couple of example problems, and they're like the classic, a train leaves the station going east, and another train leaves the station going west. This speed, where and when do they meet? And I'm going to show you how to flex using position versus time graph to solve those things, and like relying upon what you learned back in algebra class to do that. So before I get started today, I just thought I'd show you a couple fun videos of what I'm talking about. This is every weekend there's always people who are armchair quarterbacks talking about what they should have done at football games, but I thought this was really cute. It's Rich Eisen. He's a commentator. To get into the NFL, you go through what's called a combine, and you run a 40-yard dash as fast as you can. And so that's like one of the metrics with which you're judged. So they took this average dude, like I think he's like 40, probably my age, and they had him run a 40-yard dash. And then they superimpose average NFL people on top of them just to show you what superhumans that they really are.
This is you with a 7-yard head start.
So there he is. There's our commentator with a 7-yard head start. And then here comes... I mean, it's not even close.
University of Michigan, and let's pit the greatest speech ever given at Michigan by Rich Eisen against one of the great playmakers in Jabril Peppers. Here you got a 5-yard head start, Rich, and it's gone. All right, Rich. Now let's go bring a tight end in, and that's Evan Ingram. We're gonna give him a.
Oh, they race him against a linebacker. This guy, or I mean, like a lineman, someone who's like pushing 300 pounds. Like, so they're, even though they're like really, really big and like just heavy people. Yeah, almost a 300-pound person. Watch this. Like, just almost barrels him down. I have another one that's kind of fun. This, of course, this takes place in Russia. It's a jet plane versus a Porsche versus a motorcycle, crotch rocket. So they're going to actually have a drag race to see who wins. So I'm going to let you guys vote first. Go ahead and put your vote in. All right, now let's see how they do. Oh, the motorcycle thinks they have it. Interesting. And then one last one. This is I don't know if you've ever, these are Baja trucks. It's something, then they go flying across the desert. They've got 850 horsepower, and your average person doesn't understand, like, what does that mean? Like, my truck out there maybe has 100, 200. So, I mean, these things are really powerful. But then next to it, it's a top fuel dragster, and that has 10,000 horsepower. So, like, these are just outside the normal realm of people. So this thing just hammers it and goes down the track as fast as it can go. And it's probably worth 3 or 4 of my trucks. But then when you see it on board the truck, then you realize just how fast these things can go. In that quarter mile, kids, they consume 10 gallons of fuel. Like, I can't even pour out 10 gallons of fuel from a container in the few seconds. They go 0 to 60 in less than 1 second. Like, in 0.6 seconds, they're going 100 miles an hour in 1 second. And, like, it's just insane what's going on physics-wise inside of these vehicles. But on to the questions here. So the first question says, Mr. Hare, and I'm conservative here. I'm probably around Usain Bolt really as far as speed, but I run at 8.3 meters per second. Usain Bolt, 12.3. So this is 27.44. I mean, this guy can run at 27 miles an hour, which is pretty incredible. We'll give Mr. Hare a 55-meter head start. So that's think about a 100-yard dash like I'm starting midway through. A, how long does it take Usain Bolt to catch Mr. Hare? And then B, where does Mr. Bolt catch Mr. Hare? So let me talk to you about how I would go about solving a problem like this. The secret here is a position versus time graph. And you may not think of this right off the bat or whatever, but I want to show you how I would solve this problem using a position versus time graph. So I'm going to make some axes here, and I'm going to put time down here. I'm going to do it in seconds because this is in meters per second. And then over here, I'm going to do my position. I'm going to do that in meters because this is also in meters. So here you go. You got Mr. Hare. Mr. Hare's a slow mover, but he starts here at 55 meters. So Mr. Hare, slow moving. And Usain Bolt, he's a fast mover, and we start at the exact same time. So he's going to start like this. Now, if Mr. Hare had both a time and a distance head start, you would start it like that. Now, I'm starting kind of on the more less complex end, and I'm having them start at the same time. So then here's Usain. So what we're going to do is we're going to write an algebraic expression to model these lines. And so Usain Bolt's is actually the less complex of the two. His is y equals, the slope is his speed, 12.3x. Now, you probably know that from algebra class, y and x. I want you to get away from y and x, and I want you to use something like displacement equals 12.3 times the time. So here's the equation I'm actually, it makes more sense, and you'll see why in a second. So Mr. Hare, he's over here. Mr. Hare is y equals, the slope of my line is 8.3 x plus my y-intercept, which is 55. I want you to use this equation because the y is the position, so it's d equals 8.3, and the x value is time, t plus 55. So now what I'm going to do, I'm going to set these two quantities, these two equations equal to each other, and then solve for the letter t, I think. So I can set them equal to each other because they are both equal to the letter d. Since they both equal d, I can set them equal to each other. So I'm going to go 8.3 t plus 55 equals 12.3 t. I'm going to subtract 8.3 from both sides. So then I get 4. That's nice. And that's going to equal 55. I'm going to then divide both sides by 4. So 55 divided by 4, using significant figures, is 14 seconds. And I know that it's seconds because I get t equals, right? So time equals 14 seconds. If you used x's and y's, you'd end up with x equals 14. And that x doesn't really tell you, it doesn't make sense. Is x time or is x distance? If you replace the x and the y with the d and a t, it makes your solutions coming out a little bit easier to interpret. So part A, how long does it take Mr. Bolt to catch me? It takes him 14 seconds. Part B, where will he catch me? Now what I have to do, I have to put this back in to either one. I have to put this into here or into here, and that will tell me both. Because right here, this is where I'm going to meet at 14 seconds. And I can plug it into either equation that's going to give me the answer. So it's easiest to put it into 12.3. So I take 14 times 12.3. So when I multiply those together, I get 170. with my significant figures. So what this is saying is, if this was me versus Usain Bolt in a 200-meter dash, and you gave me a 55-meter head start, he's passing me in the home stretch well before the finish line. Here's a clever way to use a position versus time graph to solve these quote-unquote difficult story problems that involve velocity, position, and time. Let's do another one. Another example. So this time I changed it up a little bit, and I don't have them starting at the same time. So example 2. A car leaves Madison at noon, heading towards Platteville at 40 kilometers per hour. A truck leaves Platteville at 12:30, heading to Madison at 65 kilometers per hour. How far from Platteville do they meet? Assume that Platteville and Madison are 110 kilometers apart. Let's get started. First thing I'm going to do, I'm going to make myself a position versus time graph. I'm going to label my axes. Time. I'm going to do this in hours this time, because this is in kilometers per hour and it's at 1 o'clock. Those are hours. So over here, I'm going to do my position, and I'm going to do these in kilometers. So pick my units and stick to them, and make sure that whatever they give you in the problem matches those units. Like if they gave me meters per second, I got to change it into kilometers to make sure everything jives. All right, so I'm going to think ahead a little bit here, and it says, assume Platteville. It wants to know how far from that's important, knowing how far from Platteville. So I'm going to make Platteville the origin. I'm going to make Platteville where 0 is, and I'm going to make Madison up here. And don't go dividing this into 110 equal parts. Just put a dash somewhere and then put 110. That's where 110 is. So, which one leaves first? The Madison one leaves first, heading towards Platteville. So, there you go. This is the car. Leaving Madison at noon. I'll make this 1 o'clock. So the car starts at noon, and then it's heading towards Platteville. Now, my truck starts at 12:30, so it starts right here at in Platteville, so that's the Y, and then it starts at 12:30, and that's the X, and it's heading towards Madison. Notice how I just make my stuff, I just draw my lines, and then I force the numbers to fit them. So there's the truck, there's the car, and I'm interested in this point right here. So I'm going to write equations for both of these lines. The less complex is the car, first of all. So I'm going to write the equation for the car, and that's y equals negative. The car is going at 40. So negative 40x plus 55.
Mr. Bill Wagner, please call the high school office. Mr.
Negative 40x plus 110. So the truck, well, I'm going to change this around. Instead of y, I'm going to use my position. Instead of x, I'm going to use time. So here's my equation that I want to use for the car. Now the truck, a little bit more complicated. Because when I write this, the truck, it's going to be y equals, the slope is the speed here, 65x, and then the y-intercept. This is what gets a lot of students right here. The y-intercept is actually down here. You have to figure out where it crosses the y-axis. And this takes a little bit of creative thought. So, I know this. I know that in 1 hour, I go 65 kilometers. That's what it means to go 65 kilometers per hour. So if I'm going half an hour, in half an hour, I go half of 65, which is going to be 32.5. So my y-intercept is over here at negative 32.5. I'll do that one more time in case you missed it. I know that this is at 0, and I also know that I'm going 65 kilometers an hour. So when I go half an hour, I go half of 65, which is 32.5. And that's how I got that y-intercept. So change the letters around the variables so they make sense and help you out in the end. Displacement equals 65t minus 32.5. So here's my other one. I'm going to set these two things equal to one another. So 65t minus 32.5 equals negative 40t plus 110. That negative is really important because when I bring it over here, it's 65 plus 40, which is 105. And then I'm going to bring this over here, 142.5. So now I solve it for t by dividing both sides by 105, and I get t equals 1.2. Now 1.2 what? 1.2 hours. Is that my answer? It's not. I wanted to know how far, so you got to be careful. One of the biggest mistakes that people make in these is you find an answer and you think that you're done. Oh, the answer is 1.2. No, that's hours. Like if I said to you, how many miles is it to Dubuque? And you said 20 minutes. No, I wanted to know miles. I don't want to know time. So that's where it's really important to do these problems with the letter t, because you end up with t equals instead of x. And what does x mean? I don't know, but I know t means time. So how I'm going to find how far away? I plug it back into either one of these equations. So let's just plug it into this one because it's right there. So how far? It's going to be negative 40 times 1.2 plus 110. So negative 40 times 1.2, add 110, and that turns out to be 48. 48 what? 48 kilometers. So we end up crossing here at 1.2 comma 48. So it takes 1.2 hours. So that's like 1 and then 0.2 of 60 is 12. So it's probably 1:12 p.m. they end up crossing. Because be careful, this is 1.2. That doesn't mean it's 1:20. It means it's 0.2 hours. So 0.2 times 60 is going to get you that answer. And then it's up here 48. That's where they cross. So this is how I leverage position versus time graphs to do some pretty complicated problems. When you get a story problem, feel free to, pictures are everything. Like making a picture that is helpful in disseminating is really important.